At some point I have questions about the lecture notes. Is your file?
For file.
Yes, for
Not
file.
the one for last week.
I just have a question about this particular relationship right here.
Is everything set? Yes. The recording. Okay. Yes. Let's begin. So today we're starting a bit late. Sorry, I had technical problems this morning. My iPad was totally out of charge and ran around. Alright, so hopefully everything works. Okay, so today we're going to continue what we started last time, which are greedy algorithms. Okay, so before we go there, okay, so just something to remember, homework 2 is out and it's due this Friday. I saw that for homework 1 there were a lot of questions on Piazza, but for homework 2 there aren't that many. Hopefully you guys have all started and so on. So yeah, so that's feel free to ask because it will help everyone if there is some clarification and so on. That's one thing. The other thing is that the grades for homework 1 should be out. And if you have questions on the grading, you should ask Vivek. So questions, the way we grade them, just maybe I mentioned this before, is that TA split the questions of each homework and one person grades, let's say, questions 2 and 4 for the entire class. Okay, so that way it's there's a consistent grading scheme. So, but if you send email to Vivek, he'll tell you which question was graded by whom, and you can go and ask clarifications. Okay, so the contact person. Okay, and on Piazza, I posted a few general comments that the TAs had, and these were involving how you write pseudocode and things like this. But look at your own comments as well, okay, because those will contain more personalized comments for your report. So that's homework 1. All right, so let's continue where we left off last time. So we started looking at greedy algorithms. Okay, so this is a class of algorithms where, similar to dynamic programming, you have to make a sequence of choices. Okay, and you have problems where you have to make a sequence of choices, but at every step, instead of looking ahead and computing, which is what you would do in dynamic programming, in greedy algorithms, you just make the best choice based on a certain value that you define only using the current state. Okay. So at every stage you have a bunch of options. For each option you define a value. You pick the option that has the best value. So that's the general greedy paradigm. And once a choice is made, it's made. There is no backtracking. You can't go back and change something that you have done. So that's the general paradigm. And we saw a few examples last time. One was coin change, where we said that you had a bunch of denominations. You wanted to make change for, let's say, $1 or something, and then you wanted to use the smallest number of coins. We said that the natural greedy algorithm does not work for this. It's not always optimal. So it always produces some solution, but it may not be optimal. And we said that there are some problems like scheduling, at least the base version of scheduling that we saw, for which greedy is actually optimal. Okay, so this is one of the simple cases where greedy is optimal. And then we started looking at the set cover problem. We almost finished the analysis, but there was this last chunk remaining that we will finish today. Okay, so let's start by recapping this problem in a little while. But before that, some general comments. Okay. So one thing I'd like to say is that greedy algorithms are very easy to come up with. Okay, so in fact, I mean, that's probably the first kind of thing that you come up with. And it's probably because we are trained to think like that, right? Like you have a bunch of choices, you always just make a good choice. You don't compute too far ahead in ordinary life. Okay, so that's why greedy algorithms are easy to come up with. And as I said, they're usually not optimal. So you will find out that for the overall problem, maybe there was a better way of doing it. Then, and we saw examples like traveling salesman problem, set cover, and so on. Okay, and because of this, analysis is usually tricky. Okay, because it's challenging to prove that making the greedy choice each time results in a globally optimal solution. And today we'll see one example of this with the spanning tree, where the algorithm is natural to come up with. You probably have all seen the algorithms, but proving that they're correct actually takes some effort. Okay, so it's still easy enough, but it's a little tricky if you haven't seen it. So we'll see that. Okay, all right. So before that, let's recap this set cover problem that we started looking at last time. Okay, so the problem was very simple. You had n people who are on the left and a set of m skills. Okay, so these skills are numbered, let's say 1 through m, and each person has a certain subset of these skills. So the first person has 1, 2, and 5, and so on. And your goal is to pick the smallest number of people so that every skill is covered in something. Okay, so that is a person who has that skill. Right? So we said that you can view this as some kind of a sequential decision making, where first you pick one person. Just pick one person at a time. Okay, and who you pick next is the decision that you are making. Right? And so what is the natural algorithm? Right? So the natural algorithm is one where you maintain some set of skills. Okay, let's call it U. And iteratively you add the person with the most number of uncovered skills. Okay? Because you want to cover all the skills. Okay? So you say at every step, oh, okay, these are the skills I have left to cover. Okay? And you add the person who can cover the most of them. Because there is no point of covering things that have already been covered. Because all you need is one expert per skill. Okay? So this is a natural algorithm for this problem. Okay, so, any question on the algorithm before we move on? We saw this last time, but it's been 4 or 5 days. Okay. All right. All right, and we said that the way you're going to analyze this is by showing the following theorem. Intuitively, you would like to say that if there is a small optimum solution, that is an optimum solution that uses only k people, okay, then at every step, the set of uncovered skills gets reduced significantly. Okay? So, and this is what we wanted to show. Okay? And so that's what we mean by many skills are covered in each step. Okay? And that's the key idea. And this is assuming there is a solution of only k people. More formally, this is what we stated last time. Okay, so you maintain this set of uncovered skills, right? And you say that, let's say you've picked t sets so far. Okay, so you're at the t plus first iteration. Okay? And you say, let Vt be the set of skills that are uncovered at this point. Vt is empty, then you're done. Right? So you assume that Vt has some sets. And let u sub t be the size of this Vt. And what we claimed is that ut plus 1 is less than or equal to ut minus ut by k. Here where k is the size of the optimal solution. Okay. And if you remember, this was just proved by using that there exists an optimal solution of size k. So if you remember, so what's going on here is, this is, we are analyzing the greedy algorithm. So we are arguing about what happens in the greedy algorithm. Using only the size of the optimum. Okay. So it is saying that, oh, okay, just the fact that there exists a good optimum solution implies that the greedy algorithm has this property. Okay. And this is a subtle thing, right? Because you don't know what this optimum is, but you are able to still use the fact that there is a good optimum to show that you make considerable progress in this greedy algorithm, okay, which is what you're actually running. Okay. So yeah, so I'll wait for a bit to see if you guys want to ask questions. Yeah?
How we are able to come up with this equation?
Oh, so this is something we saw last time. If you want, I can recap roughly this proof. Oh, or are you saying what is the motivation for coming up with this equation? Okay, so this is something somebody else also asked. There's, how would you guess a priori that, you know, this is what you have to do, right? That this is would satisfy. Now it turns out there is no general way like this, right? Your only intuition is that trying to show something like this. Okay, sorry. Okay, so your only intuition is to say that, oh, okay, if there is a good optimum solution, then maybe I can show that I make enough progress. Okay. Now, what this enough progress is depends on the problem, right? So you try to prove some claim where ut plus 1 is smaller than ut minus something, and you try to show the best you can. Okay, and in this case, the proof kind of tells you that this is what you can show. Okay, so yeah, so in fact there are several problems where you can't make such a good progress, you can make only like a little bit worse progress. Okay, so there are problems where you try to analyze greedy the same way, you say that enough is covered at each step, but maybe not something as good as this. Okay. So this basically comes from the proof. Okay. Yeah, and this is what is tricky about analyzing greedy algorithms. Okay, the right statement is often challenging to come up with. Okay, so in fact, we'll see the same thing happen in the spanning tree example. Okay, and here it turns out that the right observation to make is this fact. And once you have this fact, the rest of the proof turns out to be relatively easy. So yeah.
Could you recap a little bit how we came up with the how we went over last time?
Oh yeah, so I can tell you how to prove that how to prove that that thing holds. Okay, how you come up with it, as I was saying, is more like you try to see what best you can do. Okay, so you want to show that ut plus 1 is less than ut minus something. You hope for the best, right? So we'll see. Yeah, let me just recap the proof that we saw last time of this fact. Okay. So what I was saying was, we have some set of people, right? And we have this set of skills. And there were some skills that were covered and some skills that were uncovered. Let's call these the ones below are, let's say, the uncovered ones. Okay, let's call this is V sub T. And you've picked a certain set of vertices so far, and those guys have covered all the other ones. Okay, so these are set 1 that you picked, set 2 that you picked, and set T that you picked. And those guys have covered all the top skills. I've just drawn the figure so that Vt is on the bottom. Alright. So now I'd like to argue that there is some person out here that contains, it could contain a bunch of others on the top, but it contains a reasonable number of things below. Okay, so this side, this is at least size of Vt divided by T. Okay, so let's call this person J. So I don't remember exactly what the notation was. Was Sj the notation we used for the set of skills a person J has? Was it Sj or Tj? Sj, right? Okay. Vt is at least Vt. So this is what we're going to prove. Okay. So firstly, do you guys agree that proving this claim implies this one? Okay, because the greedy algorithm will pick someone with the most intersection with Vt. You know that there exists one person whose intersection with Vt is at least size of Vt by k. So the greedy algorithm will pick someone who's at least as good. Okay. So note that there may be many such J's, right? And your greedy algorithm will pick the best one who has the most intersection with Vt. So all you have to show is that there exists one Sj such that Sj intersect Vt is reasonably big. So I see some people are not convinced, so I'll just wait until you. Yeah.
So just to be clear, the size of Vt over k is the optimal selection that we'd like to make, but because we know we don't have the optimal algorithm.
No. This is at least how much the algorithm is going to make. Okay. So and that's what we're going to show. Okay. Because so what is the algorithm doing? Right? At every step it has a Vt, and it picks a J that has the highest overlap, whose Sj has the highest overlap with Vt.
That's the greedy algorithm.
That's the greedy algorithm, right? And what I'm saying is, this is a very myopic argument, right? It's just saying that at this step, there is some set you can choose so that you cover at least Vt by k of the uncovered guys. Okay? So how I prove this statement is irrelevant to us. Okay? I'm going to show it by some means that that this is true. Okay? But assuming this is true, do you believe that the greedy algorithm satisfies this property? Right? Like the set of uncovered vertices is now at most at least reduces by ut by k. Okay. Yeah, so the subtle thing, so I'm going to wait for a, for a short while. Do you agree?
I guess I'm trying to wrap my mind around what the UT over K actually represents.
Okay, so Vt and Ut are quantities that are functions of the greedy algorithm.
And I've got
They have nothing to do with what the optimum is.
Right, okay.
Now, Vt is set of skills uncovered after picking T sets in the greedy algorithm.
Right.
And Ut is just a number, it's the size of Vt.
Right.
Right? Now, what I claim is that Ut plus 1, which is the size of the uncovered set after T plus 1th iteration of the algorithm, is at most Ut minus Ut divided by K, where K is the value of the optimum solution.
And that's the problem I'm having right there. You say K is the value of the optimum solution,
Which you don't know, but you know that it is some K, right? Right? So, I mean, the value of the optimum solution is something. So, you would like to show that the algorithm does not pick more than K times log n sets. Okay? So, you just assume, suppose the optimum value was K, then Ut would have reduced by at least so much. You don't know how much actually it reduces by, right? But you know that if the optimum value is K, it would have reduced by at least so much. Right? So that's the argument. Okay, that so at least that is the claim. Okay, and the way you show this is now by saying there exists some J such that this is true, and some set J. Now, of course, J cannot be somebody whom you already picked, because you know that then it would not have any adjacent to Vt, because Vt was the set of uncovered. So J will be somebody whom you have not picked, and so we are going to argue that Sj, that there is some J such that Sj intersect Vt is at least that. And the proof of this fact used the optimum solution. Proof of this the optimum solution. And we are allowed to do this because this is just some existential claim that you are supposed to make. Right? You just want to show that there exists some J that satisfies this problem. So I can use anything I want about the set system. Okay. So do you want me to go over this thing that we did last time, or should we just accept this for now, that there exists some J, and then continue with the rest of it? Might be good to just assume this for now, and you can go back and read a more detailed thing of this, okay? Because it's a somewhat subtle thing, and yeah. Okay. But let me tell you how this claim leads to what we want. Okay? So if you know that Ut plus 1 is smaller than this, then I claim that this procedure can't go on for too long. And the proof of this is actually relatively simple. Okay, so it says that Ut plus 1, you've already argued, is always less than or equal to Ut minus Ut divided by 3 for every T. And Ut is the number of uncovered skills after suppose you've established this bound. Okay. Now the right hand side is what? So the right hand side is just ut times 1 minus 1 over k. So now again you can do some kind of a plug and chug over here, right? You just plug this in and you get that this thing is less than or equal to ut minus 1 times 1 minus 1 by k squared. This is less than equal to so on. So overall, this is less than equal to u1 or u0 times t plus 1. So ut plus 1 is less than or equal to u0 times this thing. Okay, because it's decreasing by a factor of 1 minus 1 over k in each iteration. So after t plus 1 iterations, it must have been at most u0 times whatever that factor is to the power of t plus 1. So this is just straightforward algebra. Any questions? Right. So now what is u0? It's the whole set. Yeah, so this is exactly M. It's the whole set of uncovered things. So this is equal to M. So what you know is that ut is less than or equal to M times 1 by k to the power. And now this is, when does this quantity become less than 1? So if this quantity becomes less than 1, it has to be 0, right? Because ut is an integer. Okay. And for what t does this value become less than 1? Right. This is some calculus basic, some calculus exercise, right? So what I'm just asking, I have this this quantity, for what value of t does this become less than?
I'm not sure. I think for positive values.
Yeah, it has to be positive first. T is always positive. But I'm just like if t is 1, right?
Okay.
Then this is m times 1 minus 1 over k, which is probably like m or something. It's definitely not. It's not too small, right? So t has to be somewhat large for this term to become less than 1 by m effectively, right? So do you see what? Yeah. So think of like, if it helps, think of k as 10 or something, right? So if k is 10, then I'm asking if I have some big number m, and I have 0.9 power t, for what value of t does this become less than 1? I mean, we've seen calculations of this sort, in the sense, if this were half, then we've seen exactly this. If you want this to be less than or equal to 1, then it's like basically t being log n. But now you don't have a half here, you have like this 1 minus 1 by k. Okay, so yeah, right. Yeah, again, this is all basic calculus. So you want m times 1 minus 1 by k to be less than 1. And so we use this standard approximation. How many of you have seen this identity, or roughly seen some point in life? Okay, so hopefully all of you have seen it at some point. Okay, so you know that 1 minus 1 by k power to the power of k is like 1 by a constant. Okay, t is basically 2.7 something. Okay, so if I set t to be equal to k, then I would get m divided by e, which is like a constant reduction in m. Okay, from m you became m divided by e. Okay. So now you can guess that, okay, so let's, so if we were to set t equals k times something, let's call it some alpha, then m power 1 minus 1 by k to the t, this is now like, so this would be equal to m times 1 by e power alpha. 1 by e is just a constant, so you can think of it like the same calculation I did before, right? To think of it as half or something. So then, if this has to be less than 1, we need m less than, or alpha is more than log m to the base. Therefore, overall, need to set t to be equal to k log m to the base. So this is just the natural logarithm. Okay, so log to the base e is just a natural logarithm. Okay. And this is it, right? So this was the claim. I think my claim was a little bit incorrect to start with. It wasn't log n, it should have been log m. Okay. So if once you set t to be k log m, you become less than 1. Okay. And that's it. So that means that this procedure cannot go on for more than these number of iterations, because at this point ut would become less than 1, and ut is always an integer. If it's less than 1, it's 0. That means you've covered all the states. So any questions? So if you didn't follow this part, this is just straightforward math, but modulo that, if you wanted, if you have questions, then feel free to ask. Yeah?
What does m represent?
M is a number of sets, right? So M is the number of skills that you had to start with. So M was right. So M was the number of skills that you had to cover. Initially, nothing was covered, so U0 was M, and yeah. So that's why I wrote U0. What is U0? And that's equal to M, and that's what. Yeah.
So it's essentially like we're solving for the base case.
Yeah, it's basically like solving for when you would get this quantity to be less than 1.
Okay. So why didn't, I guess my intuition would be to just use algebra to calculate t in terms of m and k.
And that's exactly what we did, right?
Oh, okay. I guess
I mean, you could do the same thing. You would get log m to the base 1 minus 1 by k. And this is not, I don't know, at least this looks a little unsatisfactory, right? What does log m to the base 1 minus 1 by k mean?
Okay.
So this is exactly equal to k log m to the base e.
Gotcha.
So yeah.
Makes more sense.
Yeah. So I mean, you can't a priori compare this with k if you didn't know. Yeah.
I didn't catch why we wanted to define for when it's less than 1.
You want to what? Sorry?
Why are we trying to find it for less than 1?
Oh, that's because so this procedure goes on until until this Vt is empty, right? That until you've covered all the states, which means ut equals 0. Okay, but you can't solve this for ut equals 0 because then t has to be infinity. But we know that ut is an integer, so if it's less than 1, it's actually 0. Okay, so that's a mild trick that we see. Yeah, so that's a good point. Yeah. good. So let's move on. Okay. So this completes the argument. Okay, so this shows that this procedure only ends up with k log m iterations, which means that overall, if your optimum was k, you ended up with like k times log m sets. Okay, so greedy was bad, but bad by only by a factor of log m. Okay. So that's the general conclusion. So the conclusion is this is the end. The conclusion is that greedy is not optimal. Not terrible. Okay, so this is very qualitative, but off by a factor. So that's what we mean. Okay, so it's not like the greedy algorithm will end up picking all the sets or something very bad like that. That's that. Alright, so let's go on to a different example. And this is something which I'm guessing all of you have seen this example before, but let me define the problem anyway. So this is called the problem of finding spanning trees. Okay? So what is the question? Okay, so it's a very simple question. You are given a graph. It's an undirected simple graph. Simple graph just means it's not duplicate edges or self loops or whatever. And this graph has some edge weights, WE, assume they're all positive. And your goal is to pick a subset of the edges, okay, so that all the vertices are connected to one another, by which I mean if I only use the subset of edges that were picked, there is a path from every vertex to every other vertex. Okay, only using the subset of the edges that I've picked. And you would like to minimize the total weight of the edges that you have picked. So actually, just to think about it intuitively, it's in some sense, if you think of the graph as representing some nodes and some connectivity, then you want some kind of a communication backbone, right? Like you want every vertex to be able to talk to every other vertex. You want to pick a set of edges, the smallest set of edges that allow you to do that. Okay. So if I had all of these vertices, then the edges that I've picked is one such example. Okay. So this is if I draw only the edges that I've chosen, maybe this is too big an example, but if I only draw the edges that I've picked, it looks something like this. Okay. So it looks something like this. So, and all the vertices are included, and I can get from any vertex to any other vertex only using the edges I've picked. Okay. But note that if I drop this 9 and then I can no longer reach 6. Right? So suppose you did not pick this edge, okay, then you can no longer reach 6. So is the problem clear? So you have a bunch of nodes. You want to pick some edges so that now after just using those edges, everyone can talk to everyone else. Okay, so there's a path from everyone to everyone else. And your goal is to pick the set of edges that has the least total cost. Okay. And again, the reason you care about this is that there may be many solutions and you care about the one with the least cost. Okay, like a trivial example, just think of just think of, let's say, a triangle. Suppose this was your original graph. Now, how many edges should you choose here? So what would be a good solution to this problem? Okay, so you have to be able to connect everyone. So you need at least one edge out of each person. So you can have this, or you could have something like this. Is also a valid solution. Okay, but this one has, so this one has cost of 9, and this one has a cost of 7. Okay, so this is better. So that is better than this. So, and in a more complicated example like this, there are probably lots of trees that you can have, lots of ways of picking edges so that everyone is connected. So of those, you want the one with the least sum of edges. Okay, that's the problem. And as you can imagine, this shows up in a lot of places where you want to build a road network or a communication network, and you want to pick things that are of small total cost, but you want to be able to connect everyone to everybody else. So there must be a path from everyone to everyone else. Yeah.
Just a clarification on the total weight.
Uh-huh.
Is it from a certain vertex to another vertex?
No, so this is just the total weight of all the edges you've picked in your solution.
So like in the example that you've given, it would be more optimal to pick the edge between 4 and 2 instead of 1 and 2.
Which one? In this example?
Yeah.
Between 4 and 2 instead of what? Sorry?
1 and 2.
Yes, exactly.
Okay.
So what I drew here is not the best spanning tree. It's just a spanning tree. But as you observe, that's great. Okay, so here, if instead I did not choose this edge and I picked this guy, then this would still be a spanning tree because you can still reach everyone from everybody else, and this would have a cost of like 3 less, right? Because Okay. So yeah, it's a good observation. So anything else? All right. So now, how do we come up with what would be a natural way to solve this problem? Right? So you want to pick a set of edges. So it makes sense to view it as picking one edge at a time. If you had to do this, how would you pick edges?
Yeah. Start with the edge with the lowest weight. Just work your way up until you've covered all the nodes.
Okay, so yeah, it's a candidate algorithm. Your objective is to minimize the total weight. So you start with an edge of the least weight and keep adding edges. Until you forward. So this is a natural algorithm, right? So here, can you guys think of potentially bad examples for this? Oh, okay. What is a bad example?
Well, if you've already got 2 nodes covered with 2 short edges, but there's a third edge, it's also small, but both vertices are already covered.
Yeah,
so
it's always nice if you come up with an algorithm and instantly realize the issue with it, right? So this has one somewhat seemingly fixable problem. Okay, it is that you could have vertices like this where you have 1 and 2 and 3. Okay. So if you just keep adding small edges, then okay, you will add one, you will add this one, but there's no real point in adding two because those two endpoints are already connected, right? So you don't need to add that two. Reach this vertex from one endpoint from the other. Okay? So keep adding edges. Okay. While adding UV check if U is reachable from V. U is also and add only so this is a natural fix for this algorithm, right? So I mean we don't know if this is a fix, but this is at least locally a patch. Okay, so it gets over this problem, right? So is this algorithm clear? So you start with an edge least square, keep adding until you've covered all the vertices, but don't just add edges. When adding, just check if this edge is redundant or not. Right, so this turns out to be one of the candidate algorithms. So add edges one at a time, choose midway edge that is not redundant. Okay, so this is called Kruskal's algorithm, and this is a natural greedy algorithm, and turns out this is actually optimal. And note that it's by no means obvious that this has to be optimal, right? Because you're just adding edges, hoping for the best. But globally, maybe there was a much better solution, which didn't have to proceed in this manner. In fact, here's another algorithm, which so that's the one we'll analyze today because it's related to what I'll do in the next class. So, but yeah.
I don't understand how the two algorithms are different.
Oh right, actually that's a great exercise. Like you can, yeah. Actually, let me describe the first algorithm first, and then we can get to why these are different. Right? So the first algorithm says start with any vertex, start with some vertex, and so let me describe it in this picture. Okay, in the picture on the left. So you start with some vertex. Let's say I started with this guy. And think of this algorithm as trying to build a set of connected nodes. Okay. And if that set becomes the whole set, then you know that everybody is connected and you stop. Okay. So that's what this algorithm intuitively tries to do. And initially, the set is just this green set, which consists of one vertex, any vertex. Now, I want to add one more vertex to this set, so that now I get a connected set of size 2. So, what vertex should I add? Should I add? So, there's only two choices, right? I can either add this guy or I can add this guy.
Probably the shortest one.
Okay, so you add the one that you can connect with the least cost. So I add this one and I pick this edge. Now I want to make it I want to make it a connected set of size 3. I currently have a connected set of size 2. And I want to add one edge so that I bring in a third vertex. There's only one vertex, so in this case there's no choice of vertex. But I can pick one of the two edges. Again, I pick the shorter edge. So this is a natural choice. And this ended up with the solution that we decided. So let me describe this algorithm. And this is called Prim's algorithm. This is another common approach. An algorithm is just the following. Start with S1 equals some vertex. Let's call it some u. Anyway. Okay. So let's, for the picture, let's think of this as your initial u. Now I want to grow the set size by 1. Okay. And the cheapest way to do it is to add the smallest edge out of u, right? Going from S1 to the rest of the graph. Right. So in this case, there were 3 edges out of u. So those are this edge, and this edge. Of the 3, the 6 is the cheapest one. So I will add that. All edges go out of S1 and the least at the one with the least weight. Okay. And now you add whatever vertex you got to S1. Now S2 equals the set 5 and 3. So in this example, let's just set 3. So now S2 equals the set 5 and 3. And now you look at the whole set S2. So now you look at the set S2. Now I want to add one edge that goes out of S2. Now I have plenty of choices, right? There's the edges that go out of 5. There are the edges that go out of 3. And if I want to increase this set by 1, I can add any of those guys. So for example, 3, 5, 6 is a candidate solution. But this will result in this new edge having a cost of 11. But if I had 3, 5, and 0, then the new edge would only have cost of 5. Okay, and likewise, if I had 3, 5, 1, then the new edge would have a cost of 9, and so on. Okay. So the candidate choices at this point are candidate choices are for S3. Something like 3, 5, 6, 3, 5, 4. Actually, 3, 5, 4 is possible by 2 means. One is by adding the 8 edge, one is by adding the 15 edge. But yeah, you will only add the 8 edge. And 3, 5, 1 and 3, 5, 0. Now, of these, what is the cheapest one?
0.
Yeah, so of these, 350 is the cheapest because you can build that with just adding that 5 edge. Okay, so is this clear to everyone? Example. So you're building this connected component one vertex at a time. And ultimately you hope that the connected component reaches the whole thing. Alright, so this is the algorithm. So formally the overall algorithm. So V is always the set of vertices, right? And then at each step, for n minus 1. So you'll do for n minus 1 steps because you have to grow n minus 1 times. Right? You start with one vertex and you have to reach all n vertices. So you have to grow n minus 1. Consider all edges going out of S1. So these are edges that go between, out of ST. Consider all the edges that go out of ST. These are edges that go between one vertex in ST and one vertex outside of ST. And pick the one with the least cost. One of the least weight. Add the solution. Then you increment set ST plus 1. So ST plus 1 is ST union that one vertex that got added, okay, which was the other end point of that edge. Yeah, so let me just draw a picture of the map so that this see what's going on. Okay, so ST is some set of vertices that you have so far, and you look at all possible edges out of ST. Some vertices may have multiple, and each one will have some cost. Pick the one of the least cost. Okay, let's say it is this one. Okay. And this will be between some vertex in ST and some vertex outside. Okay, so suppose the vertex outside is some x. Okay, then ST plus 1 equals ST union. Okay, so this is that. This is what I mean by incremented appropriately. Okay. Alright, so this is the algorithm, and this results in ST plus 1 being ST union 1 extra vertex. So any questions for that? So this algorithm may look a bit more complicated than the other algorithm that we discussed, where you add edges one at a time and think. But if you think about it a little bit, this involves a step of checking redundancy, which may be computationally a bit more expensive, right? Well, I mean, there's a way to do that fast, but a priori that could take a while, right? While this algorithm, even as is, all it does is you have a set of vertices, and you add one at a time, and you have this list of edges that you maintain, you pick the least cost. So this turns out to be implementable much faster. So, alright, but anyways, so that's one nice thing about this algorithm. So any questions on the algorithm itself for most of the analysis?
For this one, we also should check if we don't have any filter, right?
You don't need to, because you're always implicitly looking at edges going out of ST. Okay. So you don't have to. But that's a good one. Yeah?
This is faster than the previous one.
As such, as stated. Okay, there's a way to implement both of these so that they're equally fast. Okay. Yeah.
I'll ask the same question whether you stated that both are optimal in terms of what the solution or
So when I said both are optimal, it's in terms of both return the best solution. Both return an optimal solution. Yeah, and depending on how you implement it, one may be faster or slower than the other. So optimality, I just mean both are correct in terms of they both find the best solution. Yeah.
But MST it can be unique in a graph, right?
No, so there can be lots of minimum spanning trees.
Okay.
So yeah, so I mean, because edge weights are not necessarily all distinct, right? So there can be lots of different.
So suppose they are distinct, would both of the algorithms find the same MST?
Oh right, so this was the question we started with. I forgot to explicitly state that. So it turns out if you run these algorithms, you can actually find very different MSTs depending on the graph. Okay, so because, and you can imagine, right? One somehow seems to go with picking the least cost edges, and it's going edge by edge. It doesn't care about what the vertices are. The other guy is starting with some vertex and it's slowly adding one new vertex, and it's picking edges that are locally some least cost ones. This one seems to be doing a much more global sorting of the edges and doing something. Okay, so yeah, and in fact, you can come up with these sort of examples. In fact, in this example itself, you will realize that there can be multiple minimum spanning trees, because there's lots of repeated numbers, right? So there's like 5s repeated, 7s repeated, and you know, depending on the order in which you pick them, you can get different solutions. One nice property that turns out to be true is that if all the edge weights are distinct, then there's a unique minimum spanning tree. And this also is non-trivial because, you know, even if all the weights were different, there can be different ways of summing the numbers up to lead to the same cost, right? Like you can imagine that if you had edges like of weights 2, 7, 3, 6, then 2, 7 sums to the same thing as 3, 6. They're all distinct numbers, right? But interestingly, this sort of thing doesn't happen. Okay, so if all edge weights are different, you have a unique minimum spanning tree. So, yeah, but these things in general can give very different trees. Alright, so how do we prove the correctness of this procedure? Because this is this simple, greedy building up a solution kind of a thing. So, alright. And the main thing is that, okay, so this is a simple property of the algorithm. Just by definition, you have some set of connected vertices. Set ST you have at every step is of course connected because you are always building a connected component. Right? You can reach any vertex in ST from any other vertex in ST. So what you might hope for is a claim of this kind. So you can claim that the set of edges we've added so far is a minimum spanning tree for ST that you have. Right? You're building up this set of vertices, which we are calling ST. Slowly you're adding one vertex to it and so on. And remember this picture, right? So ST is this. The next time ST plus 1 would be this guy union this one vertex. And you can imagine that, oh, okay, I had the best solution here, I picked the least cost edge out here, and maybe this is the minimum spanning tree of ST plus 1. Right? So this could be a candidate way of showing that this process is optimal. Right? But what is wrong with this argument? Actually, do you see the candidate argument that I'm trying to say? That so I would like to say that this thing, and I would like to prove this by induction. And the way I would like to prove it is to say that, oh, okay, I've picked some edges so far, and I have some edges I've picked so far. This is my ST, and I'm adding some new vertex so that this edge is as low weight as possible. Now I'd like to claim that so let's label these vertices. So this is, let's call this U1, U2. U4. And you can say that, okay, I just chosen so far. Suppose you had this property. Okay. So note that there could have been other edges here, but we are saying that those were not chosen. So edges chosen so far form the minimum spanning tree for the set that you have currently. Then I would like to claim that we have this amount here. Like to claim that adding this edge, which we call it gives an ST for set U1, U2. This would be a natural inductive proof, right? Trying to show something like this. And one thing I'd like you guys to observe is, why is this not as such true? Okay, like you can say, oh, okay, this was the best tree for this. I added the least cost edge to U5. So if I had a different edge to U5, that would only be a higher cost than this one. Okay. And why is this not a valid proof as is? Yeah.
There can exist an edge from U5 to somewhere that's not an ST that you haven't considered.
Right, so maybe there was an edge here.
Not an ST.
Oh, not an ST. So that is fine, right? All I would like to claim is that there is that what I've built so far is a minimum spanning tree for this set of vertices. Only on this set. You're right in that the optimal MST could have included edges that are outside. I don't care about the optimal MST for the full graph. I only care about for this graph induced by U1, U2, U3, U4, U5. So I have this property and I keep having this property, then I would get that even in the end. But, yeah.
We have to make sure that the minimum spanning tree for 5 vertices can be constructed with the minimum spanning tree from the 4 of those vertices. Because there's not, but there could be some other minimum spanning tree that looks nothing like the one of the 4 vertices that includes the 5 that happens to be.
So is that point clear? So what he's saying is, in trying to make this argument, I'm trying to say that, oh, this was the best tree for 1, 2, 3, 4, and now the best tree for 1, 2, 3, 4, 5 looks like this thing plus an edge. But that need not be the case at all, right? Like you could have some tree where maybe U5 is connected to this one and somebody else, and now you can drop some of these edges here, and maybe that results in a better tree. Okay, so this could technically happen, and we don't have an argument for ruling that out. Okay, so in fact, this argument turns out to be messy. This statement turns out to be true, but it's a very it's more messy to argue. So instead we will argue by something that gives more structure. Okay, so the problem with this argument is that we don't have a good structure, right? So good structure for MST of what? Of U1. Okay, so you don't really know that how the tree for all 5 things looks like. Need not be built by these guys plus an edge. Yeah.
So are you saying that the candidate claim is true, but it's hard to prove, or it's just
Yes. So in this case, it turns out to be true, but it is provable by a more involved argument. But yeah, so actually, the more involved argument will be essentially what we will see next. but yeah. So I mean, but what is lacking in this attempted proof is some kind of a structure, right? Like you don't have a guarantee that edges that you've picked so far are actually good. Maybe they all have to be removed and the total tree is different. So instead we prove a stronger claim, and the claim would be the following. Okay? So the claim would be that there exists a minimal spanning tree for the entire graph that contains all the edges that you've chosen so far. Okay? So this is a stronger claim as the claim goes, right? It's not talking about only the set of vertices you've chosen so far. It's saying that I've picked a bunch of edges so far, and I'm going to argue that there's a minimum span tree for the entire graph that contains all the edges that I've chosen so far. Okay? So at step 1, I will have that, okay, if I had picked just this edge after step 1, then I know that there is a minimum spanning tree for the entire graph that definitely contains this. And in the next step, if I pick this guy, then I know the choices so far are actually great. Okay. And if you think about it, this gives you structure, right? This tells you that you don't have to go back and change things that the choices that you've made in the past. Okay. Because that's one thing we're not allowed to do in greedy algorithms. Right? You can't go back and change stuff. So what this is saying is like a formal proof that allows you to do this. So this is the claim. Right? So now, as you can imagine, proving this claim can be tricky, but once you have it, it's nice because now the inductive step can hopefully be easier because you just have to argue that okay, I know that all the choices I've made so far are correct. I just have to make sure that the next choice is also fine. So this would be the key claim. We will prove this by. So any questions on the claim itself?
Yeah, so when we have a full graph, we can have minimum spanning tree, right?
Yes.
So if this is the case, we cannot say that it contains all the edges chosen so far.
Right. So that's why the statement is that's a good point. The statement is carefully chosen. It says there exists a minimum spanning tree for the full graph. So not all minimum spanning trees of the full graph might contain the edges that you've chosen so far. So his question was there can be many minimum spanning trees for the full graph. How are you saying this? So yeah. Right, so that's So let's try to prove this claim. So the base case is let's make it a very easy base case. Okay, so this is one where nothing is selected. Base case is going t equals 1, but this has no edges. Okay, so nothing to prove. So let's now look at the inductive step. So what this means is you've chosen some edges so far and you have some SP. So you have some SP that looks like this. Could be empty also, but it has at least one vertex. But you know that there is a minimum spanning tree for the entire graph that contains all of these edges. That's the inductive hypothesis. And you'd like to show that what you are doing in the next step, you're adding one edge like this, right, which is the least cost edge among all the edges out of this set. You'd like to show that there is a minimum spanning tree for the full graph that also contains this edge. Okay. So let me introduce some notation. Let E1, E2, Et minus 1 be the edges so far. And let Et be the new edge that we are considering. So these are some E1 up to Et minus 1 some order. This edge, this is what the algorithm is currently at. And what we would like to show. And this is what I call the optimum prefix property. Okay, so it's just the name, it's self-evident. So knowing that there is an opt tree that contains E1 to Et minus 1, we need to prove that there is an opt that contains E1 to Et. So this is the inductive statement that we need to prove. This is just the induction. Okay. So we are out of time, so let me stop here, but it's just a couple of days, so we'll come back to this when we start. We'll start with this claim next class.